in case IDE. All right. Right. So let's start with the partial derivative. So this is partial. What's called partial. All right. Try to remind you about derivative of one variable. Uh, prime. That is, let's see. Let's see how it defined. So you compute this difference of a value of uh, f of x, and x is slightly translated x plus h divided by the uh, how the displacement. Okay, or similarly, you can say that this is f of y, this difference over this. So difference in a and y minus difference in x. Okay, over this. All right. So this is one variable. The question is how to adopt this definitions to for function of two or more variables. Okay. So we attempt to copy the definitions for functions of more variables. Okay. All right. So let's see. The thing here is that so if, for example, uh, two variables. So there you go. And you can say that this is f sending to a function called z, f of x, y. Okay, so you can think this is a pair of numbers, or you can think this is as a vector. Or you can think this coordinate or a vector. Here's the number. Okay. All right. So let's copy this one here. So if we write something like this, then the x should be a vector, right? And h also, because you add something to a vector, then this should be a vector. Okay. And you divide by h, meaning that you divide by a vector. So this the first problem that you stumbled with. Okay. So this is the first is problem where we attempt to copy these definitions. That is You have division by factor. So on top you have a number because x and h are factors. But if you apply f and then the value are numbers and you see this difference of numbers. Okay. So this is number, and but this is a factor. So you have division by factor. And you can define factors. Uh, Factor division is okay. So 1/2 of a factor, for example, that is 1/2 x, 1/2 y. Simple. But you cannot divide number by factors. Right? Cannot divide numbers by factor or factor by factor. Okay. So our attempt to copy this a definition failed. Okay. So this attempt. So turns out we cannot copy these definitions, meaning that cannot copy these definitions. For derivative uh, function with two or more variables. All right, so that's the main problem. Okay, so we start with something simpler than that. Okay, now let's pretend. Uh, so let's do. So we let f to be a function of two variables. And this is a number. So factor goes to a number. Okay. So let's pretend this is just one variable by fixing the other one. So pretend f is one variable only by fixing one variable and vary the other one. So what does it mean? So this one. So fix, for example, y equals y0. Okay. So what we have is and vary the x. Okay. So what we have is this x. Okay. Or we can write this down as this doesn't mean power though. It just means that we fix the y naught, y0. Okay. So it's just a function of one variable. Okay. This is one variable. So as a one variable, we can define a derivative. A one variable functions. We can define derivative as usual. Okay, so what's the derivative? So derivative is because this is just a function of x, function of variable x. So we can take this derivative ddx, okay, of, okay, so this is the limit of this difference plus h. Okay, minus f. Okay, and this quotient is now defined. Why? Because h is number. So this is just regular definition of limit of derivative. Okay, so that's so. So what does it mean? So this is actually x. X goes to 0. You see this one? So f has two variables, but when we add h, when you translate the xy, you translate only one variable, it's only x here in this case. Okay, and similarly, we can fix the other one. Uh, you fix x equal x0, and you vary y, and you can take this derivative. Okay, so this is the limit of, see, this is x0 fixed and y plus h. Okay, y5 h. Okay, so this is what we call the partial derivative, the notion of partial derivative. And the word partial is now clearer, I guess, because you see it has a two variables, but when you take derivative, it just apply to one of the derivative. And the first examples only applies to x, and the second example, the derivative only applies to y. Okay, so this is called partial derivative. Okay, and as partial derivative, this is called, this is notations, the x, the f over the x. Okay, and this one here is the f over the y. So you slightly change the notion of not the notions, the notations d, instead of doing this, but you change the d. Sometimes you heard it, people call it dou f dou x. And the same thing, df dx, but partial. Okay, partial derivative, meaning that you take derivative only one variable. While keeping the others, because you may have more than two variables, others fixed. All right, so let's do some computations. Let's do some examples. So we don't need a more rule how to compute partial derivative, because uh, let's see, x of this, for example. Okay, first derivative of this one here, x squared plus y squared. Okay, you take derivative only to x. Okay, so we take derivative only x, so only this to x, to x. And in this case, y squared is constant. Okay, uh, constant with respect to x. So that's why the derivative of constant is 0. So this term is constant with respect to variable x. Therefore, dx of y squared is 0. Okay, so any symbol other than x is treated uh, as constant. Any other symbol other than x are treated as constant. Okay. All right, so let's see what about this one here. Sine xy, for example. Or let's see, let's make it slightly different. So not to make it x, this is y squared. Okay, let's see. When you take derivative of this, uh, let's see, x is, you think x is a constant. Okay, so when you take derivative of this, sine become cosine. All right, the same angle. So angle is xy squared. And then times, because of the chain rule, you get to multiply this by the derivative of what's inside. But the derivative of what's inside is, with respect to y, is just 2y times the constant. The constant is x. So you get this one. Okay. So we don't need the separate rules for computing partial derivatives. Okay, so we just use the um, rules for derivative for these just one variables. Okay, therefore, all the formula for derivatives applies. Right? Uh, we don't need extra or special rule for partial derivatives. Okay, so let's just do some more examples. So let's pick up some examples from the textbook. To computing. All right, so let's. All right, can you see the problem set here? So problem 1 to 16, for example. Okay, let's pick something. Let's say uh, number 6. So this one here. Oh, find the so this is the first partial derivative of this function, 3x squared plus y squared power 1 negative 1/3. This is called the partial derivative. First partial derivative. Okay, so let's see. This is respect to x. Okay, so you think y squared is constant. Okay, so in this case, going to be, let's see, using power rule, you know that the power will decrease by 1, so it just become 1/4. And because the chain rule, you gotta multiply by the derivative what's inside. In this case, partial derivatives. Right? So you get 6x into y squared, that's 0. Here we go. That's the derivative. Okay. And don't bother to simplify. Okay. Here you get the same thing here, similar. Uh, by chain rule, you gotta multiply by the inside respect to y. So I think the x squared just constant. So now you gotta multiply by 2y. Okay, so this is the first derivative. Let's do something else. Okay, now let's compute the second derivative. What does mean second derivative? We'll see. Um, tangent inverse x, y. All right. So before going to that one, let's do second derivative. So what's second partial derivative? Second partial derivative meaning given f, you compute this one. This is first derivative. The second is let's see. This is second derivative. All right. For example, x, and then you take derivative with respect to y. Right. So meaning that take derivative of x, or the other way around, you can, meaning you take partial derivative with respect to x of df dy. Okay. Apart from those two, we have also Well, that's now clear. This is ddx of ef dx. So second derivative with respect to x. Similarly, dy of ef d uh, yeah, dy. Okay, so you have four kinds of them. Of fourth, no, no, second partial derivative. Okay, so all those combinations. Let's find the uh, give some example of this. Or find all first and second partial derivative. Okay, so let's see. Oh, f. F is given by tan inverse x y squared. Okay. All right. First derivative respect to x. Think y is constant, so y squared is constant. So tan inverse derivative is just 1 over 1 plus square there. Okay. And because of the chain rule, we got to multiply by what's inside. So the inside is the angle. Sorry, not angle, just number. Right? So ddx of this is this one here. Take derivative with respect to x. So y squared is constant, so it just becomes constant. Okay. While derivative, partial derivative with respect to y, that's the same as this. But derivative xy squared with respect to y. So x is the constant in this case. Derivative is just 2xy. All right. Is it clear so far? Questions? All right. Now let's say the second derivative. Okay, so derivative dx dy. That means you're taking the derivative of this one here. So that means take derivative ddx. Let's just write this down. What is of this one here? So just write this down to xy. Okay, respect to x. So think other symbol than x as constant. So y squared are constant. Okay, so we get here, let's see. This is a quotient, so I use quotient rule. Okay. So derivative of top respect to x, just y, times this. Okay. Right, one. Yeah. This is is this correct? Yeah, that's correct. Right, 2xy. Yeah, times derivative of this one here. So derivative of this is with respect to x. Okay, so one, no, derivative of one, that's 0. Okay, and derivative of this squared is 2 x y squared as derivative of this respect to x is y squared over and square it again. Not complicated. Okay, but and we don't bother to simplify if the problem doesn't ask you to do that. To do so. All right. Now derivative of the x dx. Okay. So this is the dx of df dx. That means of this one here. So take derivative of x y squared, that's 0, times whatever there. This is 0. And then subtract derivative of uh, this y squared times derivative of this respect to x. Okay, so this is 1, that's 0. Derivative of this is so xy squared uh, yeah, power 1 times derivative of this respect to x is y squared. Okay. Over squared again. Okay. All right. Now the dy dx. That means dy of df dx. Dy of what is this? Df dx. Okay, so derivative of this is 2y times this. Sorry, from here, xy squared, subtract 2y, derivative of this with respect to x. So this is different. Oh yeah, it's the same. Um, and last, okay, so meaning dy of dy. The dy is, let's see, what's the dy here? Yeah. And you can compute this one. Let's see. Uh, derivative of y, so just 2x times no, yeah, 2xy times derivative of this respect to y. Uh, so this is 2y times right? Looks complicated because we use one. All right, let's do something simpler in polynomial. So let's observe something else. Let's do something easier. So let's check the 17, the easiest one from this example. So let's see, where is the thing? Let me just copy. The first derivative, we have the x. That's easy. So just think x is your variables. Any other symbols other than x is considered as constants. All right, so just you have 4x times the constant y cubed and minus 3x squared. Okay. While df over dy is, let's see, so 6x squared has become y squared. So okay, minus, um, this is constant, x cubed, derivative of this, y to the fifth, 4 of them, so 4. Okay, so now let's compute this one. So that means the dx of this, df dx, okay, take derivative with respect to x. So 4y cubed, so this becomes a 6x y to the fifth. Okay, the x dy, right? So that means take the x of a df dy here. With respect to x, so you have 12x dy minus x squared minus 4. Okay, and see, let's switch the order. That means the dy of df dx is, so with respect to y, okay, derivative of y cubed is 3y squared. So it is 4x. They become 12. Okay, so minus the y, so this 5, so 15 of them. This is the constant, x squared constant, so derivative there. And last, second derivative of y. So the dy of x, oh yeah, this is y. Respect to y, so it becomes 12 x squared y. Here becomes, let's see, what's this? 4, 4, 6, 3. These constants. Okay. So one thing that you may have noticed is it's this one here. You may have noticed this one here. When you switch order, so this is dy dx, this is dx dy, this is dy dx, you get the same thing. So what will happen to this one? Okay, so these two are called mixed derivative. So in general, mixed derivative are different. Thing. Uh, but however, we have this one here. Let's see, go back to the textbook. Let's see, show you one thing here. Where is that theorem? Oh, this this is not here. Let's see. Let's look at this one. Let me just show you. We jump to next sections just to quote the theorem. Compositions. Where is that? Here's the other thing. This one. Rather technical, but let's just use it. Just put it at the moment. We'll explore later on. Well, this should be here. This one. Here, the equality of mixed partial derivative. So that's there's notations. F x y meaning dx dy. Okay, so f y x defined as dy dx. Okay, so for derivative, for this notation of derivative, we don't use the comma anymore, the prime. So because this this derivative is clear, this is first derivative, and because you have one variables, it is clear to what the variables respect to. Okay, so in this case, clear derivative with respect to x, because only one variables, the only variables. Okay, but when you have two or more variables, when you have use prime, it's not clear whether you take the derivative or with respect to y or x or z or whatever. So we use this notation here, and it's just to simplify the notations. So if you take the third derivative, you have f x x x, right? And you have x x y. You have x y x. You have y x x. You have x y y and etc. Okay. All right. So this mixed partial tells you that if f are continuous, well, continuity, will define what continuity means in the next sections. Continuous on an open set. Say it's not continuous only one, only a point. Okay. Then mixed derivatives are actually the same, right? And almost always that is the case. Our case is, say, always the case when mixed derivatives are the same. So, so mixed partial derivatives are the same. Okay. So later on you have uh, this one. That's the same as, that's the same as that. Okay. So then that's about the mixed partial derivative. Right? Okay. Questions? Show you the some more example just from the pick up from book. So let's move this again to the partial derivatives. Mm, to Okay, so this is the uh, second partial derivative. You have fxx, you have xxy, you have fyy, you have yx. Okay, so for second partial derivative of this one here. Okay. First derivative, that's easy. One. F of x, f of y, okay. Partial f, partial x, partial y. And you get this thing. All right, so let's do more computations later in the second part. It's not in just there's the questions. Any questions? All right. If not, then let's take a break uh, for 5 minutes, and then we'll continue with the second part of our sessions. All right. Stop the record.